Yeah. Anyway, so when you're doing binary to octal, octal is 8, binary is 2. Yeah. So what I have to do now, from the steps I show you, they just breaking it up into groups of 3 and ignoring leading zeros. All a leading zero is if you have like 2 zeros started, the definition of leading zero is any 0 digit that comes before the first non-zero digit in a binary number. So right here, you have a leading zero. Yeah? Seeing that? 2 zeros. Anytime you see like you have 2 zeros or any 0 digit, you just ignore it. Yeah? So you just drop this and you stop. If it had 3, you'll just drop a leading zero. Yeah? And then you have a next one, you drop like it. You just keep on going. Yeah? Nice. So now, after you drop that, you just group it into groups of 3 and convert to binary. Yeah? So octal. So group of 3, you notice this one only have 2 that add a dummy. It's like a dummy 0 if you want to call it that. So add a dummy 0 there. And now we convert into octal, right? So I'm using the same concept that we did for binary, right? Binary octal, think of octal like the decimal system, but up to 8. Remember, decimal is 0 to 9. Octal is from 0 to 7, if you want to count it. Yeah, so it's literally like a subset of decimal. So you could use the same steps that you would do for binary to decimal. Yeah, just gotta remember, you gotta group it into groups of 3, ignoring any leading zeros, and just convert it. So this here is to the power 0 to the power 1. So this here is basically just 2. Well, 3. Because yeah, the to the power 0 is 1. So it'll be 3. And this here to the power 0 to the power 1. So this here will be 2. Yeah, so this in octal is just 32 to base 8. Yeah, you just group it into groups of 3. And for each group of 3, you just slap down the binary stuff that we learn to the power 0, that's add it up, and you get a value in each piece of 3. So each piece of 3 will give you a number. So if we have 8 groups of 3, that means the octal number will have 8 digits in it. And don't forget to put this 8 at the bottom to know what base in. It's only for 10 you don't need to put it, that's understood. But for 8, which is octal, for binary, you had to put the 2, hexadecimal, you had to put the 60. Just remember that. Don't forget that. All right, this one here, same idea. Luckily for us, in this one, you don't have any leading zeros. So I could just go ahead and cut it into 3. So there's a group here, there's a group here, there's a group here, there's a group here, and there's a group here. Yeah? And as I say, that's converted. What we learned from binary. So probably could do it in your head by now. So this is to the power 0, 1, 2. So this is 4 plus 2, 6 plus 1 is 7, right? This here is to the power 0, 1, 2. To the power 2 is 4. So there's just 4. This one here to the power 0, there's 1. Then 1, 2. So this will be like 5. And put by the point, remove the point. And this is to the power 0, 1, 2. So there's 4 plus 1, which is, what is 4, 1 is 5. What this one was? Let's create 0, which is 1. Then this is 2. So this will be 6 actually. Because to the power 2 is 4. And then to the power 1 is 2. So it'll be 6. And this here is 0, 1, 2. So this is 2. And this is, well, the same thing as before. So it'll be 6. So the number in octal will be 745.66, and you put the 8 at the bottom. That's the idea. Yeah, that's the same thing over and over. Yeah, right. So, right, so I go binary to hexadecimal. So it's the same idea, but when you go into hexadecimal, hexadecimal is 16. So it have 4 groups of 4-bit binary numbers. So yeah, let's split it up. So every 4 is basically hexadecimal digit. Yeah, so just like octal, but it's just in groups of 4, you're going now. And it's not leading zeros or anything for hexadecimal when you go. So from binary, groups of 4. So there's 4 here. This one here, even though you're seeing it's 3, you can add dummy zeros to it. So don't get confused if you see like it's a 3 or 2, just add dummy instead. Yeah? Okay, you're not going to change the value because anything to 0, it's not going to change. Anything by 0 is 0. Yeah? And then this here is just one value. So now to convert, is 0. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. So 8 plus 4 is 12. 13. There's 14. This here is 0, 1, 2. So there's 2. Squared is 4. Yes, 6. And it's not going to change, literally. If I had a 0, the dummy 0, it will not change the value. Yeah? And then this one here is what? 0, 1, 2 to the power of 1 is just 2. Everything else is 0. Yeah? So this would just be 14 and a 6.2, 16. But I have a mistake in this. There's 14 here. When you write in 14 hexadecimal number, hexadecimal goes 0, 1, 2, 3 up to 9. And after 9, it have A, B, C, D, E, F. Yeah, so actually 14, if you're going from 9, A will be 10, B will be 11, C will be 12, D will be 13, and E will be 14. Yeah, so this will just be E 6.2 in hexadecimal. If you forget, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and at 9, yeah, and 10, 11, 12, 13, 14, 15 would just be A, B, C, D, E, F. 10, 11, 12, 13, yeah, up to F. Yeah, so I had 14, but I can't put 40 because 14 is not a member of the hexadecimal system. So I had to replace it with E because E is 14 in hexadecimal system. Yeah, and that is all it is. Yeah, so that's a recap. Binary to hexadecimal, group it into groups of 4. And from the groups of 4, it just converted like how we know, convert it to the powers. That's all it is. Yeah. If you notice thing odd and odd stuff, just add dummy zeros to it. And not gonna change the value. So for this one right here, that's like how we used to add the dummy zeros. You can't change the value that here. Yeah. So all you're gonna do, 110, you just add a dummy zero. So that's how we'll look. But you're not looking at that. Okay, you just convert it by just looking at it. Yeah, so this was the original number. And you just add this dummy zero here. That's a fidelity that you can actually see for, but I'm not going to change the derivation. Yeah, and that's it. Right. I think I have right this macro one here, where the same idea. Groups of 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Have a point, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Same idea. And I just convert to the base. So this is 0, 1, 2, 3. So it have 1, 2, 4, and 8. That should be 15, which is F. Anyway, so 12, yeah, so that F in hexadecimal, and not 16, F, yeah, or 15. Then that is, yeah, 12, yeah, 15. Yeah, like 15. In hexadecimal, F is 15. They can't write 15. They'll get it wrong. Just be careful, right? They can't write 10, 11, 12, 13, 14, or 15. If you had to write those, it's A, B, C, D, E, F. Remember, remember, don't make that mistake. Yeah, because you'll lose 3 marks to that. Yeah, remember 10 to 15, the number itself doesn't exist in the system. They use A, B, C, D, E, F. I don't know how much time I repeat that. Just be careful. All right. So then this one, 0, 1, 2, 3, same idea. Not no 0, no 1. So this will be 1. This here is 4. So 4 plus 1 is a 5. And this one here, so 0, 1, 2, 3. So this 2 to the power 0, they have 1 here. Nothing. 4 and 8. 8, 12, there's 13. So 13 doesn't exist in the hexadecimal system. So if you're replacing it, 9, A, B, C, will be D. Yeah. And then this is 2 to the power 3, that'll be 8. And then this one is 0. This is 2 to the power 0, 1, there's just 2. This is 0, 1, 2, 3. So this is 2 plus 4 plus 8. 8 plus put 13. We had that already. Yeah, 2 to 8, then 4, then 2, 12, 13, 14. What that would be E, there's E, 14, 15, yeah, F. And then this is 0 to the power 0 is 1, so there's just 1. So put that all together, well, that is it there. And that's pretty 690. But the idea is, yes, you made mistake with the numbers and stuff. That's okay. But the idea, or way to catch in hexadecimal is 0 to 9, A, B, C, D, E, F. Those is where we place 10, 11, 12, 13, 14, 15. Secondly, all you need to do to convert binary to hexadecimal, you just group it into groups of 4, and you convert each group to the hexadecimal form by using the same binary trick I'll show you. And that is it. Just be careful with the maths. Okay? It could cause you to make little mistakes here and there. So just be careful. Right? And then, well, hexadecimal to octal. When you're doing this, all you have to do, if you remember the little shape I show you, it have no link to go straight from octal to hexadecimal. Remember your diagram? So what you need to do, you have to use a connected flight. And the connected flight you use is from octal to binary, and then from binary to hexadecimal. Same way from hexadecimal to octal. It go from hex to binary, and then from the binary to octal. It have no steps or no way to go straight from hexadecimal to octal. Yeah? Yeah, they use binary as a connecting. You can say a connected flight. That makes sense, right? So anyway, so all you need to do, just what we did before, it is going backwards. So you need to write 2 in binary, 3, 4, and 5. Yeah? And you just use the steps that we did to convert to octal. So you're kind of going from hexadecimal to binary, and then from binary to octal. So it's kind of like two set of steps you have to do when you're doing this. Yeah? So 2 in binary. So what I like to do is like write some place values. So I'll just write, oh, at the bottom. So yes, go 1, 2, 4, 8, 16, 32, 64. Yeah, so remember octal is like 4. So like if I want to represent 2 in binary, one needs to remember there's 2 to the power 0. So I'll need 0, 1, 0, 0. Yeah, remember you need 4 digits, right? So that'll be it in 4 digits right there. 0, 4, 0, 0, 1, 0. If you represent this in binary is 2. 2 to the power 1 is 2. So let's write that. 3, if you want to get 3, you're probably seeing it here now. I could keep these 2 zeros, and this will be our 1. So, and I have 0, 0 here. 4, if you catch the idea by now, if I want to get 4, I will need this, and I don't need the rest. 0, 1, 0, 0. To get 5, I will need 4 and 1, so it will be like that. Yeah? And I heard us like convert any number to binary real quick. That's right, though, the numbers like this here. And you just kind of ask yourself, right, which numbers I need to get what number I need. Yeah? Just keep in mind the bits of the number. In this case, we're looking for 4-bit numbers. So most likely when I'm doing it, the numbers will give me 4 bits. Bits means the amount of numbers I see. So 1, 2, 3, 4 is 4 bits. Yeah? So analyze it. Anyway, so now that we convert to binary now, so I'm binary form now. Now I need to convert the binary to octal. Yeah? So there's a leading 0, so I just ignore it. And then I group into groups of 3. So I group here, group here, group here, a group here, and a group here. Yeah, so that's 1, 2, 3, 4, 5 groups. Yeah, so now that's convert to octal. Remember, that's kind of using the binary stuff, right? So there's 0, 1, 2. So that basically just 2 there. This here is 2 to the power 0, which is just 1. This here is 0, 1, 2. So you have 1, 4, which is 5. This here was 0. And this here is 0. Oh, there's 5, but we had it already here. Yeah, and just split it all together now. It will just be 2, 1, 5, 0, 5 to octal to BC. Yeah, that's what it is. Since you're just like amalgamation of stuff in already. Convert to binary and then go from binary to octal. Yeah, that's it as link the two. Yeah, and I will not do this one, but it's the same idea, right? You can try this one when I send it to you. Same idea. You write the binary for 2, 3, 4. Keep the point. Write it for 4 and 5. The binary for 4 and 5. Yeah, and once you do that, you just group it into groups of 3. Write it, convert it to your octal, and put it together. It's the same steps. And it's the same way if you want to go from octal to hexadecimal. You'll just have to write the octal numbers in groups of 3 back together. And then from there, you group it into binary into groups of 4. And then they go to hexadecimal. So that will look. So like you see, I had 8, 4, 3, 2, 8 in octal, right? So we know these numbers came from grouping it into groups of 3, remember? So you just go in the reverse back to where you want it. So this 8, we could express 8, 2 to the 3, 2 to the 2, 2 to the 0. Yeah, so this would that be 1 here, and you have a 0, 0, 0. Yeah, so let's write it. Let's write it back. The 8, let's write it back. So this will be 1, 0, 0, 0. And do the same thing for the 4. 4 will be what? 0, 1, 0, 0. And the same thing with 3 will be 0, 0, 1, 1. And 2 will be 0, 1, 0, 0. 0, 0, 1, 0, sorry. Yeah, and then you have it in binary. And obviously you know how to convert to the hexadecimal now. Yeah, because it's in groups of 4 already. Let's use the same trick you did before. Yeah, it's the same idea. Once you get, you're not gonna forget. Just don't leave out the point if you have it. But anyway, so that's the recap to figure those things. So again, so what we wanted to do, which is binary addition and stuff. It should be simple for most of you all, but I'll just go through it quickly. Right? So we shouldn't spend too long on this. So adding binary, we know 1 plus 1 is a 0 in the column and it carry the 1 across. Yeah, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. Yeah, so okay, let's show you the examples, right? So the first one here, 1 plus 1 is 0 and you have a carry. Think of it as when you like add two numbers and you get more than 10, you just like write the number outside and stuff. So 1 plus 1 gives 10, 0, and you put the 1 there, it's the same idea. So when you add 1 plus 1 is like you have the result is like 10 when you're doing it, which is 10. Yeah? Cross so the 0, put the 0 here and the 1 that's with it. If you don't want to do that, you don't need to. When you add 1 and 1, 2, the number 2 doesn't exist in binary. 0 and 1, right? So you'll get the 0, put the 0 here, and you carry the 1 across. If you forget that, just put the 10 outside, cross the 0, put it here, and you add the 1 to the next column, which is what you're accustomed doing. Yeah? So anyway, so I continue the question. So we have 1, 1 plus 1, same that earlier. Yeah, so 1 plus 1 is 0, and you have a 1 here, right? So here now you're noticing, well, you have 3, but it's the same idea. Yeah? We know what this 1 plus 1 here. That's this 1 plus 1. Okay, I have 1 here and 1 here. This here, you know 1 plus 1, you have a 0. So this here gonna give you a 0, and you have to carry a 1. Yeah, so you kind of like doing it in groups of 2. You can't just group all 3 one time. Yeah, so this 1 plus 1 here will give you the 0, and the 1 you carry, and now it just has 0 plus the 1, which is just 1. Yeah, that's the idea. Even if you have 4 groups of 1, you would just have to carry 2 groups of 1. So like if I had this here, this will give me 0. I want to carry a 1. And this here will give me 0. So I have to carry a next one. Yeah, and the overall answer will just be 0 plus 0, which is 0. Yeah, so that's how you just think about it. Each group of 2, 1 plus 1 is a 0, and you carry a 1. Once you remember that, you can carry more than one thing from the same column. Just remember that. Yeah, it's a little different when you do it. So you can't write 4. Yeah, you can't write 4. So back to what I was doing here, 1 plus 1 is 0, you carry the 1, 0 plus 1 is 1. Same thing here now, 1 plus 1 again, which is, that is 0, and you have a 1 to carry, and now you have 0 and 1, which is 1. Yeah, and this side, same idea, 1 plus 1 is 0, we carry a 1. So the number will just come. Yeah, that's the idea. The only thing I have to remember for this is 1 plus 1 is 0 and I carry a 1. If you have three ones, you just do two group of ones at a time, get a 0, carry the 1, and just go again in the same column. Yeah, that's really what the idea is. So this one here now, 1 plus 1, 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 0 is 1, and then 1 plus 1 is 0, we carry a 1, and well, 1 plus 0 is just 1. Yeah, that's really all this is. That's all it is. Yeah, the only thing you have to remember when you do these kind of thing is that 1 plus 1 is a 0 in the column, or the 1 plus 1 is a 0 for that result, and you have to carry 1 across. Yeah, you could do that an infinite amount of times in a column. So just to bring home the point, all right? I was trying to bring it to that was what to catch it. If I had 1, 1, 1, 1, 1, 1, some mad thing like that. This here give me 0, carry a 1. This here give me 0, carry a 1. This here give me 0, carry a 1. And then you add where you're left with, you get 0 in the column. Yeah, you will know. Yeah, that's really what it is. So you will notice as a trick, if the amount of ones you have in the column, if it even, you will always get 0 as a result. Yeah, but if it's odd, the one will be the result, and you actually have to carry a 1 across, which makes sense. I'm gonna show you why it makes sense. Because if I have 1 plus 1 plus 1, right? And in the decimal system, we know this is 3. Yeah, we know that 3. Hopefully everybody know that 3. But in the binary system, for adding these three together, 1 plus 1 is to give me 0, right? And I have to carry a 1. Yeah? So now I have 0 plus 1, which is 1, right? And then this one could be added to, well, just to get 1. But watch this. If I was to convert this number back to decimal, right? This is 0 and this is 1, right? Watch it. 2 to the power 0 is 1, right? And 2 to the power 1 is 2. And where's 2 plus 1? It's 3. So the equivalent is the same thing. Yeah, it's the same thing. It will all give you the same answer. And that is actually a cool way to check and see if you answer correct. Like when I was doing the exam, what I did, I just convert this to decimal and convert this to decimal at the top and then convert it back to binary because I stronger going from decimal to binary now. And I kind of didn't remember how to do it in the exam. So what I did, I just convert it so the two to the power 0, 1, 2, 3, 4, and you could just add it up, get back the decimal number, same with the bottom, add it up in decimal form if the answer is 52, and I show you how to convert from the decimal back to binary and you get the zeros. Yeah, so that's like a way to check over your work. Yeah, but the idea is, or way to catch is that when you add two ones, you get a 0 in the column and you carry out. The trick is if you're adding an even number of ones, you will notice that the result is always 0. And you carry the amount or double up. So what I mean by that is two ones, 0, and you carry 1. So each pair of ones is a carry you had to do. If you notice the pattern. So this one pair, you carry 1. This here is one pair, carry 1. This here is 3 pairs, we carry 3. And the result was 0. Why? Because it was an even number of ones. But if it was an odd number of ones, it's the same idea for the groups of 1. But you realize that the result is 1. So like if I was to erase this last one here, you'll end up with an odd number of ones. Because 1, 2, 3, 4, 5. So the result, obviously, will be 0 plus 0 plus 1, which is 1. And you'll get 2 pairs of ones carrying across. Yeah, so that's something to keep in mind that you could use just in case you need to. Yeah, nice. That binary addition. Let's add it. All right, so subtraction now. Similar, but the thing you have to remember when you're borrowing, because you're in a binary system, you could only borrow 2. Yeah, you can't really borrow anything else. So let me show you what I mean by when you're borrowing, you borrow 2. So like if let me show you. So like 45 minus like say something in the decimal system. We notice that 5 can subtract 7. we will go to 4, go to 3, and we'll carry across 10. Yeah? Normally I write 1 and it see it as 1 and 5, which is 15, right? But the reason why we use to carry across 10 is because we will need decimal system. Yeah? So that is why we carry across 10. Now, in a binary system, when you borrow, you're still subtracting 1 by carrying across 2. If it was in an octal system, when you borrow, you're carrying across 8. Yeah? So just keep that in mind. Once you remember that, it resumes. When you borrow, just like in the decimal system, you borrow 1, you get 10. In the binary system, when you borrow 1, you get 2. If you're an octal, if you borrow 1, you get 8. Yeah? If you're in hexadecimal, if you're subtracting a hexadecimal, when you borrow, you get 16. Yeah? That is the, or F, if you want to call it, be technical. But anyway, so I go through this one. So we notice we can't subtract it, so we have to borrow 1. So there's 0, and this is 2. Yeah? So 2 subtract 1 is 1. 0 subtract 0 is 0. 1 subtract 1 is 0. Right here, I can't, so I have to borrow 2. Yeah? And 2 subtract 1 is 1, and well, this will be 0. And that is the answer. That is it. Just remember, when you borrow, you have to borrow 2. Yeah? Because you're in a binary system. Bi means 2. Yeah? That's essentially all it is. Um, this one here, same idea. 1 minus 1 is 0. Here I need to borrow. Borrow 1. Go to here, get 2. Yeah? 2 subtract 1 is 1. This will be 0. 0, and 1 minus 1 is 0. Yeah, that is the idea. Yeah, I think I have one more. So, same idea, right? This one here, this one here. So I need to borrow from this one, right? So it's the same idea. So I'm going to do one that you're accustomed so you can see the link. So let me say I have this, right? Actually, that's supposed to be a 0. Right. So let me say, start from it. 5, can't subtract it. So I used to be, I'll go to the 0 and you realize, well, 0 and nothing. So I'll go to the 3 and you'll be like, all right, 3 subtract when you get 2. You used to write 9 here and you used to write the 10 here, right? But it's the same concept in binary. When you go down, every time you go, you gotta keep on subtracting 1 as you go down the root. Yeah? So if I try and borrow from this one here, it'll be 0, and it'll be 1 here, and it'll be 2 here. Yeah? That's the idea that you're looking at. Yeah? That's what it is. Really and truly, that's literally what it is. You will just keep on going 1, 1, 1, 1, 1, 1, 1, 1, straight on to the last one. Same idea for this. If it was 3, 0, 0, 0, 5, 99, you will have to go to the 3, and you have 9, 9, 9, 10, same idea. And then you'll be able to do the subtraction. Parallel to that, it'll be 1, 1, 1, 2. That's what it is. So this question here now we could go ahead. 2 subtract 1 is 1, 1 subtract 1 is 0, there's 0, 1 subtract 1 is 0. And that is the answer. What I need to remember with the subtraction, when you borrow, you're borrowing 2. Understand? Just like by decimal, you're borrowing 2 for binary. Secondly, if you notice, you have to borrow across zeros. It could be 1, 1, 1, 1, 1, 1 until you reach where you want to go to, which is the 2, which is the ending result, right? And that is all it is. Yeah, that is all it is. Right. Multiplication, I mean, I don't want to teach you how to multiply, but all I will tell you for this, just treat this like how it does multiply normal numbers. Yeah, it's not going to change at all. Let's have no catch, no trick, no thing I remember for this. How your primary school teacher teach you how to multiply? Just use the concepts. Yeah, this one you could legit put it in a calculator. Can you? Yeah, but no. If a calculator could work in binary, yes. Yeah, but this one you have addition part. So that's why you needed to know how to add before you could learn how to multiply in binary. Yeah, come on, when you multiply, you have to multiply both of them when you add the two results. So you have additions. So so if I start with this one here, so it'll be 1, 1, 1, 1, right? Go to the 0 here, you have 0, Then you have 0. Well, everything could be 0. Yeah, and this one here now could be 0, 0. Then you have 1, 1, 1, 1. Yeah? So add the tops together. And look at that, we just learn how to do binary addition. So this here will be 1, this here will be 1, this here will be 2. Yeah, but remember, it will be a 0 and a carry a 1, right? Yeah, and then this here is 3, so we know this and this will give me a 0 and I have a 1 to carry across. 0 plus 1 is 1, right? Or if you want to use the trick, there's an odd number of ones. So I have one group of 1, so I'll carry a 1 and the result will be 1. Yeah? Anyway, so now I have 1 plus 1, which is a 0, and I carry a 1. And I have 1 plus 1 again, which is 0, and I carry a 1. So that'll be the answer again. So it's multiplication and some addition. Yeah, and that is it. That's all it is. It's like normal multiplication. The only thing you have to remember is how to add any binary system. Yeah, and that is it. Yeah, so that is also wanted you to know for binary, how to add, subtract, and multiply. Yeah. All right, so let me run across. So I wanted to go through. So the new piece now that I had to go through, and which we'll go through this week, is how to deal with negative numbers, right? So your computer, everybody know your computer is with ones and zeros, right? So because of that, if you have a negative number, the computer needs to know how to read it. How does the computer know that a negative number there? Yeah? So now you're gonna learn about something called signed binary numbers. All I mean by sign is that 5 and negative 5, you can't use the same code for it. You have to know there's a negative and there's 5, or there's positive and there's 5. What we used to use before is unsigned binary digits. Yeah? Meaning it really matter. Don't have a sign to it. I'll show you what I mean by that. So the signed ones, what has happened is they add a bit specifically to let you know, all right, there's a negative and there's a positive. A specific bit. And that bit is called the most significant bit. If that confusing you, the bit on the furthest left of the number is the most significant. And the one on the furthest right is the least significant. Why? Because if I have a 4-bit number, so I say 0, 0, 1, 0. If I wanted to know the values for each place, we know this is 2 to the power 0, right? This is 2 to the power 1, 2 to the power 2, and this is 2 to the power 3, right? This here has a place value of 8. This here has a place value of 4. This is 2 and this is 1, right? So this here is the most significant bit. Okay, it holds the largest value. Even though it's 0, it has the largest place value. Yeah, and this here is the least significant bit. Why? Because it's the least of the bits. Yeah. So you can legit think of it as the biggest and the smallest. Yeah. So that's where let's go. If you figure that the number that you don't know, the first digit is the most significant bit. The last one is the least significant bit. But how does it? If so asks you why, there's the explanation. When you convert it to decimal, the 0 will have the largest place value. That is why it's called the most significant bit. But anyway, what has happened in the sign when you add a negative now? Have a bit, which is the most significant bit that is used to let you know that is a negative, right? So then we get into something called the signed magnitude. And you can cut it in half. Sign and you have a magnitude. So let's go into that one. So just like I told you, right? To express negative and positive numbers, which way your computer uses, the 0 as 0 is used for a positive number. And a 1 is used for a negative number. So how it goes, the number on the furthest left hand, or I can use the most significant bit now, is the sign bit. And the other numbers is the magnitude. By the way, we'll use to convert to whatever digit. Example, if let's say I had ins, they will legit tell you in signed binary code. They have to explicitly tell you it is signed. Okay, if they don't say it is signed, that means it's like normal binary, meaning it have no sign bit. Yeah? So example that I'll do it in 2. So like if I have 0, 1, 1, 1 in binary. 0, 1, 1, 1 in binary. This is signed. And this is unsigned. So what's the difference? How do these sign first? So this sign, 0, this bit here telling me the sign. So it's positive, right? Yeah? And then the other bits now will tell me the value or the magnitude of the number. So this here, I just go and convert to binary. So there's 0, 1, 2. You don't convert the sign. All this bit telling you is if the number positive or negative. It have no value. Yeah? If you can let it cover it, and the numbers that are remaining is what you convert into decimal, right? So to the power 0 is 1, 1, this is 2, and this is 4. So it's 4, 5, 6. So this will be 7. So this here, 0, 1, 1, 1, and sign BCD, binary code, is positive 7 in decimal. Yeah? But look at the difference. Now we in the unsigned, meaning that's 0. Yeah, 0 has a value. Yeah, even though it is 0, it has a value. So this will be 0, 1, 2, 3. Look at the difference. You notice in this one, the 0 had no number. Stop at the 1 before it. This one I included because it's unsigned. And you need to remember that. That's such a trick. You have real easy. You have to, anytime you say signed, just know the first bit, giving you the sign. Positive or negative. 0 positive, 1 negative. Remember. Yeah, and obviously this will be the same value. But even though there's 0 here, that means the 0 has a value. Yes, it's still 7, but it's just 7. It have no sign. This is just 7. This is positive 7 because this is a sign. And this is just on sign, just 7, flat 7. Yeah? So all this sign magnitude is, the first bit is the sign, the rest of the digits is the magnitude. That is literally how it does go. There's no difference. But you have to tell you it's signed, how much time I repeat that? You have to tell you it's a signed. So let me say, so say is a signed 6-bit number. So a signed 6-bit meaning, so let me say 0, 1, 0, 1, 0, 1, right? So since you said it's a signed 6-bit number, that means this 0 here telling me the sign of the number. And the other 5 bits giving me the magnitude. Yeah, so this will be positive, and then this one, you convert it. I'll show you that now. We can convert it. 0, so it will be 1, so 0, 1, 2, 3, 4, 16, 16, 2, 18, it'll be 19. So it'll be positive 19. Yeah? Yeah, that is all. That is all it is. Once you remember that, signed magnitude, sign, and a magnitude. The first bit is the sign bit. That's what I call it. And it is the most significant bit in the binary number. And the other digit is the magnitude. That is where we'll convert to get the actual number if you want to convert it to decimal or any other code, right? So I just run through, I'll just do two for right? If I want to convert 13, so in sign magnitude, right? I need to get it into binary. Yeah? So all I'm gonna do, I just add the sign bit after. So like our custom 1, 2, 4, 8. I think that's enough to get it in, right? So I need 8, I need 4, 8, 9, 10, 11, 12. I don't need 2, I need 1. Right? So all I need to do to this to get it to be a signed binary number, let's add the sign bit. So it's positive, right? So it'll be 0. Yeah? Analyze it. So it'll be 0, the sign. So positive 13. Signed BCD. Yeah? Same idea for 20. I could use these numbers here. I'll just add 16 to it. Because I might need the 16. So to get 20, I need 16 and 4. So I need 16, no 8, 4. So that is 20. And to get to be positive, I just add the sign bit, which will be 0. So that'll be it. 0, positive, 20, binary. If it was negative 20, same idea. There's 0 here, let us be our 1. Yeah, that's really what it is. Yeah, right. So even if they went in the opposite, like say they didn't give you 20, and they just wanted to ask you, okay, what number does this represent? Given that this is a signed binary number, all you know is, forget about that, that just saying positive, and you just go and convert this to decimal, and you get your value, and you'll end up with positive 20. Yeah, and that is what. Once you remember it have a sign bit, we get through. Yeah, well, we try that one. Now 4 would be 2, so it'll be 0, 0, 1, 0. Well, 0, 0, 0, 1, 0, 0. Right? And then you add these zeros, so it'll be 0, 0, 0, 1, 0. Yeah, is the idea. Even if I mix up the numbers, that is the idea. Yeah. That is the second to last one, the sum called ones complement is the easiest thing you ever do in your life. All this is, you're just inverting the ones and the zeros. It still has a sign, but yeah, it still has a sign, but all these are sign BCD numbers. So it still have a sign. Yeah, so 45. If I wanted to get the ones complement of that, or seriously to do it, same thing before we convert it. So what do we need? So we need 1, 2, 4, 8, 16, I think 32. I think that's enough to get 45, right? So 12 we need 32, plus 8 is 40, plus 4 is 44, plus 1, which is 45. So I'm gonna need the 1, I don't need the 2, I'll need this 4, I need this 8, I don't need the 16, I need this 32. Yeah? All we need to do is add these sign bits. Positive, so it'll be 0. Yeah? So this number in the sign binary will be 0, 1, 0, 1, 1, 0, 1 to base 2. Yeah? And if you had to get the 1 complement of that to express it as a negative number, this is how your computer will know, okay, there's negative 45. Yeah? They will kind of see the 1's complement. You could program a computer to know how it will distinguish negatives. I think computers, they work in something called 2's complement and the 1's, but the sign magnitude is like the basis of everything, right? So the 1 complement of this, it just invert the 1's and the zeros. That's literally what it is. So 0 become 1, 0, 1, 0, 0, 1, 0. And that is the 1's complement. You just invert the 1's and the zeros. Yeah, that's all it is. Yes, that's all it is. Yeah, if I want to do 23, like you say, it was, yeah, like it 23. So if I can, I can use this on top. Well, I'm gonna need 16, 4, 2, and 1, right? So I'll need 1 here, 1 here, 1, 0, 1. Add the sign bit, 0. So it'll be 0, 1, 0, 1, 1, 1, these 2. And then 1 complement, let's invert, so 1, 0, 1, 1, 1. Yeah, 1, 0. Yeah, well, 1, 0, 1, oh, extra 1. So it'll be zeros at the end. 0, good. Yeah, so make a mistake there. Anyway, so that's it. So this here is negative 23. This here is 23. You have to know what it is. Yeah? So your computer will see this as negative 23 in the ones complement system. So you can actually program a system to in the ones complement way. So it will read this at the bottom here as negative 23 and what on top as 23. There's the ones complement of it. Yeah, so just be careful when you're doing it. Yeah, they have to tell you what system you're in. Yeah? And the same thing for 8. For 8, it'll be the same idea. Right? So you can try that one and I send it to you. And the last thing for the day is the 2's complement of a number. Right? All this is the steps, you invert the bits, that's how we did before, and you add 1. That is 2 steps. It's nothing more. It's like 2 steps to remember, right? So for the 1's complement, you invert the bits. And for the 2's complement, you invert and you add a 1. So 2 steps instead of 1. Yeah? 1's complement is 1 step. 2's complement is the 1's complement plus 1. Crazy, you got 2. Anyway, so that's how it does work. So if I convert in 45, well, it's the same number, so I could just use the same thing as before, right? Well, 45 was 0, 0, 1, 0, 1, 1, 0. So 0, 1, 0, 1, 1, 0, 1. All right, so if I had to get the 2's complement of this, first thing I invert the bits. So I get 1, 0, 1, 0, 0, 1, 0, and then you add 1. So you add 1 there. So 0 plus 1 is 1. And this will be 1, 0, 0, 1, 0, 1. Yeah? Now that is the 2's complement. And this is negative 45 in 2's complement form. If you go and convert this to binary, well, decimal, you will not get negative 45. Yeah, your computer sees this as negative 45. Yeah, so if you actually go to convert this, it could be like, but sir, there's negative 17 or something. Yes, but your computer, when it's programmed to see the two's complement of a number, it will just do the reverse of what you put in, and it will know that it's actually negative 45. Yeah, so just be careful. Yeah, this is the two's complement of this. So this says 45, and this down here is negative 45. Yeah, it's just how they express the numbers. So how the computers work is they will just go backwards to know what the positive number is. And since you're sending the two's complement, it will know it's the negative of that. So they go backward. They don't read what you're sending. Yeah. So 23 was the same idea. So what 23 was 0 1 0 1 1 1. So 0 1 0 1 1 1. So I do invert the bits 1 0 1 0 0 0, and you add one. So you have 1 0 0 1 0 1 base 2. And there's negative 23. Yeah? And that's it. That's literally it. You can try 8 base up. So what we went through two's complements. It is ways to express negative numbers in computers, right? So I went through the ones complements. We went through the basis of the sign BCD, which is the sign magnitude. So it have a sign, which is the most significant bit, the number on the furthest left-hand side, and then the other digits or the other bits is the magnitude. So that way we'll get the magnitude of the number, and then the fourth bit is the sign of the number. Yeah, so that is ways to express decimal or negative numbers, right? Because your computer reads positive and negative numbers. It just don't read 7 and 8. Yeah, so that's really how your computer does see numbers. It may be one or multiple, depends on your system, right? So that is signed numbers, right? We did multiply, which is the same thing as normal multiplication. We did subtraction. When you're borrowing two. Addition, show you that one. And we'll recap of the conversions. Yeah, and that was it for class. Right, so I'll stop it now. Any questions? Or you're all good? All right, so if no questions, that'll be it. Next week we'll go to the last piece. You should be doing the quiz too. So we finish in lecture one next week. And we may have time to go further. So all the best. And I'll see you all in school. If anything you helped anything else, see me in school or message me, right? So all the best.